All right, so binomial random variables. N independent trials are performed. Each trial is a success with probability p and failure with probability 1 minus p. And x denotes the number of successes. Then x equals 0, 1, all the way to n. And the probability that x equals to k, that is that we had k successes, is n choose k, p to the k, 1 minus p to the n minus k. They're independent. Now, why do I see that? So for instance, suppose that n is equal to 4 and k was 2. In other words, out of 4 trials, we had 2 successes. So where does the n choose 2 come from? Because you see, we have first, second, third, fourth experiment. 4 choose 2 means choose the 4 trials, choose 2 out of the 4 trials that produce success. The remainder are failures, right? The number, then the reason we have, so p is the probability of having a particular success. So for example, item 3, it's 1/3 times 2/3 times 2/3 times 1/3. That's what it happened. I can group it as 1/3 squared, 2/3 squared, and altogether I will have, in this case, 4 choose 2. Right? Ways of arranging S's and F's. Good? Where 4 choose 2 is which of the 2 trials carry out the success, carry the success. So everybody understands why in general it's n choose k, p to the k, 1 minus p to the n minus k. They're independent, so I multiply them. Remember the multiplication rule, guys. Nobody forgets the chapter 3, right? Multiplication rule in general is not, it's conditional, right? It means probability of trial 1 being a success times probability of trial 2 being a success, being the probability that trial 1 is a success, right? But they are not affected. The probability is not affected by what happened before. So that simply remains p to the k, 1 minus p to the n minus k, and choose k. Please, hello Valeria, nice to see you. Please write in the comments if you follow that explanation so far. All I said is again x equal to k. If I have n trials and k of them were successes, then n choose k represents the number of the particular combination of trials that produce success, and that's the probability of having a particular string of successes and failures. Okay, what about the others? So yes, got it. Yes.
So Professor, each of the 1, 2, 3, 4, they're just examples of if we have n is 4 and then we have k
yes,
many successful trials.
Yes.
Okay.
Again, right? Let me just go through that one more time to be sure everyone is here. X equal to 2, where we have n trials, n equal to 4, we have n trials, and we want to know what's the probability of producing k equal to 2 successes. So how could the successes be produced? Either success, success, failure, failure, or success, failure, success, failure, or all other possible combinations. Yes. So notice that for example, 1, it's this situation, this probability is 1/3 times 1/3 times 2/3 times 2 times 2/3. Here, number 2, it's 1/3 times 2/3, 1/3 times 2/3. Yes. But if I combine 1/3 together and 2/3 together, I have 1/3 to the power squared and 2/3 to the power squared. And then I just add over those numbers. How many additions do I have? I have n choose 2, in this case, sorry, 4 choose 2 additions. Make sense? Not everybody confirmed, so I hope it makes sense to you. Yes, Naomi, yes, okay, well, I'm moving on. We can verify that the summation in general for a binomial random variable, the summation over all probabilities must equal to 1. So here it is. Remember, Chabeli, you asked me why do we need a binomial? This is the first, the binomial formula. This is one obvious reason why we will need it. So it's the summation k0 to n choose k, p to the k, 1 minus p to the n minus k. The summation is just the expansion of p plus 1 minus p to the power of n, which is 1 to the power of n, which is 1. The answer is 1. Yes? Here is a first question, guys. So screws produced by a certain manufacturer are defective with probability 0.01 independently of each other. The company sells the screws in packages of 10 and offers money back guarantee that at most one of 10 screws are defective. What proportion of packages sold must the company replace? Okay. Everybody understood the question, guys, right? So we replace it if we have more than one failed screw, right? So if we have one failed screw or 0 failed screws, we don't replace. Yes? So that is the easiest way of dealing with it. It's a simple question. Is I replace if x is bigger than or equal to 2, which is the same as 1 minus the probability that x is less than or equal to 1, which is 1 minus probability x equal to 1 minus probability x equal to 0. So it's 1 minus 10 choose 1 probability that you have 1 minus 0.99 to the power of 10. That's the probability that you have 0. And that's approximately every 4 out of 1,000. All right, are we ready for the next one? At each step, a randomly moving particle is equally likely to move 1 unit to the left or 1 unit to the right on a number line. If the particle executes a total of n moves, describe the probability mass function for the particle's new position given that it starts at 0. You understand? So it can move left or right. It started at 0. I want you to describe the mass function of where it's located based on, well, make sense? Random moves. It moves left or right randomly starting at 0. Where can it be located after n moves?
Professor?
Yes.
So by random, we mean probability was it doesn't prefer left or right.
Exactly.
Okay.
There is no preference for left or right. All right. Shall we? Yeah, so let's do it. Okay, so very simply, think about what happens here. Moving to the left is negative, right? It's negative motion. Moving to the right is positive motion. So let's consider x to equal the number of motions to the right. Okay, x equal to j is number of motions to the right. So then n minus j was the number of motions to the left. So it will be j minus n minus j. That will be the position, yes? J minus n minus j, which ends up being 2j minus n. So y equal to 2x minus n, where x is the binomial distribution, minus n gives me the position of the particle after n steps. Everybody says why it's 2 times x, because x equal to j is the number of right motions, yes? So if I had 0 right motions, that means I only move to the left, right? So I convert binomial to position. So if I have x equal to j, that means that j minus n minus j is how many units I move to the right, which is 2j minus n. Everything makes sense? So y equals to, yes? How did I get the parameters? Well, moving to the right? So I randomly move at each step to the right or to the left. So let's imagine that all I track first is how many right motions I moved, right? So right is a successful motion and left is another motion, yes? So x equal to j, the number of successes, number of right movements is binomial, right? With n equal to, well, with n trials and probability of success 1/2. P equal to 1/2, yes? And then to convert it to position is that if I moved j units to the right, I moved n minus j units to the left. I have left motions n minus j times, and altogether I move to right, to all the rights. I add the rights together and subtract all the lefts. Yes, and you get 2j minus n, which is, by the way, a good analogy. When you have too much left, you get something very negative. So what you have here is y equal to 2x minus n. 2x minus n is your position on the coordinate axis. Yes. And probability that y equals to k is 2x minus n equal to k, which means x equal to n plus k divided by 2. So the probability that y equals to the number k, whatever k we'll just investigate in a moment, right? Whatever possibility for y is, the position k, the probability of that is n choose n plus k over 2 to the power or times 1/2 to the n if n plus k is an even number, because it has to be an even position here. Otherwise, I cannot divide it by 2. X cannot be equal to a fraction. Yes, and 0 otherwise. And what could y be? Y could be equal everything left, it's minus n, or minus n plus 2, or minus n plus 4, or minus n plus 8, all the way to n. I move in increments of 2. So for example, y equal to minus n plus 2j is the same as n choose j 1/2 to the n. You understood how I solved it, I guess, more or less, yes? It's from there, it's just algebra, right? Well, the mass function probability y equal to k is just, I can convert it to the probability of x being equal to a particular number. All right, let's move on. In a certain country club, there is a popular dish which each guest orders independently with probability 0.8. Today, the country club has 100 guests. What is the probability that all of them will order this dish? You understand? So we have 0.8 is the probability that this particular dish is ordered. And each guest orders the dish independently of the other. Okay, naturally. Okay, so it's not very high probability, yeah? Not at all. So clearly preparing 100 dishes is wasteful. How many dishes should the country club prepare if the management wants the probability of running out of stock to be less than or equal to 1/1000? You understand? So they don't want to prepare all the dishes. They just want to prepare some number of them. How many should be prepared if the likelihood of running low or running out of stock is 1 over 1,000 or less. All right, let's do it together since I want to move on. So here is how we go about it. Okay, so we want the probability that the number of stakes requested, right? You don't have to finish solving it. Some people always try to give me a number, right? We want the probability of the number of dishes requested when it's m, so that the desire for more of them, desire for m plus 1 or m plus 2 or all the way to 100 will be less than 1 over 1,000. Good. It's possible to estimate this number better, but you can just I say experiment show that it happens when m is 91. Okay, so I want to make 91 dishes. You can do it in so many. Yk equal to m plus 1. So the way I did it is m is how many I made, you see, and m plus 1 is it's how many requests I have. If I get m plus 1 or m plus 2 or m plus 3 all the way to 100 requests, then I run out of stock. Good. So there are nice ways to estimate this number, but I will talk about such things maybe later, right? So you understand this is just this summation, and this probability has to add up to less than 1,000. I want m to be 91. So it's easier to do when you study approximations to the distribution. Okay. Here is another one. So it's pretty challenging question again. Maybe I will give you that question and maybe we will solve it later. Would you afterwards, right? Because I'm not sure you will come up with the answer right away. An electronic device has an odd number of identical components. You might imagine an airplane having 2 engines or, 3 engines or 5 engines. You understand that type of thing, right? So it has more components. Each component is likely to fail with probability p. The components function independently of one another. The device fails if most of its components fail. All right, so it will still work until most of the components fail. So if you have a device that has 3 components, it needs 2 components to fail, to no longer function. If you have 5 components, it needs 3 components to fail to no longer function. Yes? Then what are the conditions on P if the device with 2n plus 1 components is more reliable than the device with 2 n minus 1 components. You understand? What must be the reliability of, so the failure rate, so to speak, the failure rate of P, if it's better to have more components than fewer components. You might even have a sense of what that might be. So you might have an instinct of what P might be, but of course you want to argue to be sure that it is the right instinct. You understand? Anybody has an instinct? That just as a question to ponder about. Everybody understood my question? Yes, guys? So a device has odd many components, and each is working independently and fails with probability P. What should be true about P if it's better to have more components?
Wouldn't it be better to have more in general though, just so in case one fails, the other can pick up the slack?
That depends. Right, that's the because again here you need to have odd many components, and most of them must function for the device to still work. If most of them fail, that stops functioning. Yes, so that there are two conditions here, right? It's not that each component is going to keep working. You have to have most of them functional.
So would it be something like P has to be closer to 0 than 1? I don't know exactly what the number would be.
Yeah, but what is the break point when you prefer fewer components and more components, right? So if P is very close to 0, perhaps you imagine that you want to have more components. If they're very reliable, not likely to fail, you want to have more components.
Maybe less than a half or something?
Oh, good. So good feeling, I think. But so here is you see, I have all this blah 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 description, and 1/2 is correct. So you have good instincts, Naomi, right? But explain mathematically why, okay? Because you see, I mean, it's a good feel. What you think? You think 1/2 is the point where it might no longer matter. Less than 1/2, the device is reliable, and you want more of them. If they are reliable, more than 1/2, it's non-reliable. You want to have less of them. Kind of like this one by sort of symmetry, but the symmetry is not forced just yet. You need to argue. Good. So I'll leave this problem for you to think for later if you intend, and I will go and talk about other things. So properties of binomial random variables. Okay. So we need to figure out expectation and other things of the sort. So we want to know what is the expected value and variance of a binomial random variable. So for that, we will need to calculate the expected value of x to the power of 1 and the expected value of x to the power of 2. Okay, maybe I will leave you to do that. You can do it any way you like. Calculate the expected value of x to the 1 and x squared. Let's calculate the expected value of x. On average, how many successes will you have? You can do it, guys. We learned about expected values, how to calculate such things, yes? So expected value of x, you can do it. That's, in other words, what's the expected number of successes? Okay, Chabeli and whatnot, great. I wonder how you calculated it, of course. That's very good. Very good, Naomi, great. That's the easiest thing to do. All right, let's do it together, I guess. Yes, guys, are we ready? I don't hear from too many of you. I only heard from Naomi and Chabeli. What about the rest of you? So I actually bothered doing the calculation without using the properties of expectation, but I'm a bit too tired to go through it, right? We will. It's not useless because it makes you rehearse all sorts of good ideas, combinatorics, etc. Right? But of course, it's very, very comfortable to do that with the property of expectation. Yes. So we can do it this way. So we can define indicator variables x1 through xn, and each displays either 1 or 0 depending on the cave trial alone. The expected value of x is the expected value of the individual xk's, like what Naomi wrote. And each of them is just dealing with the, let's say, the first trial, the second trial. Each of them have the same probabilities of success and failure. So the expected value of x1 is probability of success times 1 plus 0 times probability of failure. So we don't need to consider probability of failure. So it's just p. This is p, and this is p, and this is p, and each of them is p. So we add p to itself n times, and we get n times p. The number of successes will be n times p. Good. Again, guys, I encourage you to look at solution A later on. I just try to not get, I need to gain time. I'm not sure. I'm hoping I'm keeping up good enough time to cover the material. I have a huge amount to cover. Yeah. And then what about calculating the variance? Can you calculate the variance of the binomial? Let's see if you can do that. All right. Yes, Naomi, that's right. Guys, so one person is up to it. What about the rest of you? Do you see how to do it? You can do it very easily using properties of expectation. Variance in this case, because remember we proved that variance of the sum is the sum of the variances provided the trials are independent, provided the sums of random variables are independent. So I'm going to take variance of x1, x2, xn. And because they are independent, remember there is the covariance is 0. So remember that part. So variance of x is variance of x1 plus variance of x2 all the way to variance of xn. And that's n multiplied by variance of x1. Yes? Guys, I need your support and confirmation, right? Am I doing well? Do you understand what I'm explaining to you? Or am I talking to myself? Yes? So you understand that this little formula. Variance of the sum is the sum of the variances, but not always, only when the variables are independent. Expected value of the sum is always the sum of the expected values. You understand? Make sure that you understand it, not just remember this, me saying this, but understand it. Yes? Wonderful. Now, what's the expected value of x1 squared? Remember, I'm going to calculate the variance of just x1 squared. Now, x1 squared is 1 squared multiplied by p plus 0 squared multiplied by 1 minus p. In other words, the expected value of x1 squared is still p. And how do I calculate variance? I take the expected value of x1 squared minus the square of the expected value of x1. It will be p minus p squared. You see that? P minus p squared, I can factor out the p. It's p times 1 minus p. So I have p times 1 minus p plus p times 1 minus p plus p times 1 minus p n times. And therefore, my variance for the entire random variable is np, the expected value, multiplied by 1 minus p. Do you understand how I solved it? And again, I hope you are going to look at solution A. I just don't want to cover it now since it takes time and we can do it this easier way. So here is a proposition. If x is a binomial random variable with parameters n and p, then as k goes from 0 to n, first we will see that the probability will increase monotonically and then begin to decrease monotonically. Its largest value is achieved when k is the largest integer less than or equal to n plus 1 multiplied by p. And here is how I am going to reason that out. You see, so around the expected value, this looks kind of like the expected value is where I begin to shift. Understand? Where I see the expected value, that's kind of going to be the peak, and then from there I descend. So I climb to the peak, and I begin descending. So I know that by this calculation, if I know that probability x equal to k is bigger than or equal probability x equal to k minus 1, that is only true if this ratio is bigger than or equal to 1. Now what is this ratio? It's nk, pk, 1 minus p and minus k, and this is the same for k minus 1. Yes? Then I simplify everything. And I get p over 1 minus p. Here I have the factorials cancel out. And after a little algebra, I get n plus 1 minus k over k times p over 1 minus p bigger than or equal to 1. Okay? Make sure you do this algebra, you will figure it out, right? Simple enough. And then I multiply by the denominator, and I see that I see this part multiplied by p is bigger than or equal to the denominator, k times 1 minus p, which is what you see here, right? So then I continue simplifying a little bit more. I can eliminate this. And I see that n times p plus p must be bigger than or equal to k. And that can only happen if and only if n plus 1 times p is bigger than or equal to k. You see, so I see that k should not exceed this number. If it exceeds this number, then I no longer have greater than or equal, I have less than. So that tells me that this is my peak. Good? Okay, now we talk about hypergeometric random variables. I tend to never remember the names, right? Hypergeometric, why is it called this way? All right, so suppose that an urn contains W white and B black balls. And we draw a random sample of n balls. So X is the number of white balls selected, 0, 1, all the way, right? So if the balls are drawn sequentially with replacement, then X is binomial. You agree? Because I take a ball, I note what was success or failure, and then throw it back, and now it's the same trial all over again. And it has parameters n times n and p is equal to w over all the balls, w plus b. That's the p parameter. Everybody understands that? Now, on the other hand, if we draw n balls without replacement, X is going to be called hypergeometric. And then if it's without replacement, you understand? So the result of one trial affects now the result of the next trial because I removed the possibility, right? If I failed, I removed the failure. Now it's more likely that I'll have a success next time, right? If I have a success, it will be less likely that I'll have a success again. So we will say that this is a hypergeometric random variable with parameters W that correspond to options for success, B, options for failure, and N is the sample, how many I need to draw, number of procedures carried. And then we can calculate the probability that X equal to K. Probability that X equal to K is W choose K, which of the white balls were drawn, and then which black balls were drawn. So B choose N minus K divided by drawing a random sample from B plus W. You all understand this formula, guys? So drawing them sequentially is the same as imagining that you do that at the same time. Remember, we proved that in chapter 2 or chapter 3 a while ago, right? That if you have sequential removal, it's the same as at once, right? So we have the situation. And of course, observe that if K is the minimum of Wn, then of course, the summation will equal to 1, right? Why do I say minimum of W and N? Because I mean, I cannot have more successes than the entire number of white balls, and I cannot have more successes than the number of trials. That's why it's minimum of Wn. Yes? So for instance, if we know that the sample is less than W, so in other words, I have more white balls than I'm gonna sample, then we have that the summation from K equal to 0 to N, probability X equal to K. I want to show it's equal to 1, right? It's the summation of W choose K, B choose N minus K divided by W plus B over N. And then I look at the summation, look at it. It's just a summation of picking from W plus N, picking a sample of size N and grouping here by categories. This means I have this many white balls, this many black balls. You recognize this formula? Combinatorial formula for W plus B over N. So I know the ratio is 1. Good? And this reminds me of a situation I really had. I'll tell you who are the elk. Right? A forest has N elk. Today, M of the elk are captured, tagged, and released. At a later date, N elk are randomly captured. You understand? So first, there was some day, some M creatures, elk were caught. They received a tag, maybe a nice earring, and they were let go. Now, later on, a sample of N elk are randomly captured. Assume that each of the N elk is still equally likely to be captured because they're stupid, right? So they don't really change their behavior. They're just as likely to be captured as those that did not experience the situation. What is the probability that K of the original elk are captured? Do you understand the question, guys? Yes? See if you can solve it. So we want to know, so they were tagged. K is the elk that will be that are captured again. Of course, the better question: who are the elk? Okay, Naomi. So yes, here is what we have. So probability x equal to k. It is the number of previously captured. There are m previously captured. Out of them, I choose k, and then out of the remaining ones that are not m, I need to choose n minus k. Understand? So from m, I choose k. Now those are the captured for second time. The rest are captured for the very first time. Yes? And the elk were, of course, probability students that I had a while ago from a different school, right? And what happened is I captured them because they cheated on my exam. And I released. I tagged and released them. And you guess what happened on the final? I made a very nice trap for the final. It was in class exam. And they fell into the trap. And I failed them. And one of them wrote to me, "You have done an injustice upon me. I wish you have it in this life and the next." And those were my elk. Now you know. That's why I like probability. You tell little stories about your experience. Yes? But I get old and tired, who knows? Maybe I am not gonna capture you. I hope there is no need to do that as well. Here is another question. A 5-card hand is drawn at random. The number of aces in hand is x equal to 0, 1, all the way to 4, right? And what's the probability that I have k aces? It's 4, choose k, the 4 aces I have, and the rest of the cards are not aces, and from them I have to choose 5 minus k, and the total is 52, choose 5. So that's a hypergeometric random variable. I tend to never remember why it's called hypergeometric. Maybe there is a good reason for it, but I don't know it. Okay. So the next theorem about hypergeometric random variables is that two hypergeometric random variables with respective parameters w, b, and nw plus b minus nw have the same, have identical distributions. So weird looking thing here. Let me try to explain to you what's the idea. Yes. So we can imagine this in two ways. So we have usually two tags for the elk. We have well, we have captured elk and not captured elk. So we have and afterwards we have sampled. Okay. So for balls, maybe that will be simpler for you to understand. Suppose we have w plus b balls, right? And they are initially identical. Then what we have two tags that we apply. We have a tag that is basically, you can imagine printing on the ball a stamp saying sampled, and printing another stamp on the ball which says white or black. Understand? Sampled, white or black. Two samples, right? And the reason we will have identical distributions is that we can imagine that the sampling is done non-randomly and tagging of white or black is done randomly. Or tagging of white and black is non-random, but sampling is random. And there is a symmetry between the two processes. Do you understand what I'm saying? So I can think of this problem this way. Either I sample non-randomly, and once I sampled something, it turns into black or white. All of them turn after the sample black or white, or I first turn them into black and white, and then I randomly sample. Okay, so that's the idea. Okay, so let's see what we will get. There is a symmetry, you understand? So symmetry is either random sample or either random sample and then assign the colors non-randomly, or sample non-randomly and assign colors randomly. You with me? So let's say that we will stamp W on W balls, designating them as white, and then randomly sample, what is this thing? Stamp S on N balls, right? That means S is having sampled. So then the probability that K equal to, that X equal to K is that I have non-random white balls, out of them I choose K, and non-random black balls, out of them I choose N minus K, and then I have W plus B choose N. You follow me, guys? It's a pretty clever idea. Now, there is a symmetry with this process where I stamp S. In other words, I sample the balls, they're all the same color. Can you imagine? I sampled K balls, they were all the same color. And once I finished sampling, all the balls, all the W plus B balls randomly switched colors white or black, right? And then what's the probability that I gathered K white balls? So that would be that out of the N balls that I picked, exactly K turned white, and everything, and then the remaining ones turned black, right? So then out of the remaining balls, W plus B minus the balls that are not sampled, exactly W minus K had to also turn white. Do you see what I have here, guys? And on the denominator is that any of the W plus B balls can turn white. So I'm claiming that this, or look how different they look like, but I'm claiming that those two fractions give you the same exact number all the time. Do you see that? It's a very kind of, it's a sort of symmetry, you understand, basically, guys. So I think a little bit it's like this point of view. You know, this camera that you attach to your head, it always looks like your head is fixed and everything else is moving. That's the way I think of it. Yes. So it's a matter of perspective, right? So when I sample, when I select a random sample, I can imagine I can imagine select a random sample where the colors are definite, or I can imagine that my sample is non-random, but the colors are indefinite until I sampled, and the results will be the same. Yes, the symmetry is basically, I'm using an argument by symmetry, if you understand, right? So why is that an argument by symmetry? Because you can think of the color of the ball as a particular stamp on the ball, and sampled or not sampled is another stamp on the ball. So with hyperbolic random variables, or hypergeometric, I'm sorry, I don't remember what they are called, you have two stamps. One of them is sampled or not sampled. The other one is of a particular category or not. With the elk, it's captured or not captured, and the other stamp is you captured prior or not captured prior. Okay, and I can choose which of those I want to be random. One of them has to be random by symmetry. That's what I'm saying, right? So it's a symmetry argument, of course. Yeah, I hope you see it. It's what I will need it for what I describe over here. So properties of hypergeometric random variables. So can you calculate the expected value of a hypergeometric random variable without me helping you? Right. So so let's do this. Okay. So the hypergeometric random variable, I'll write it here. You have parameters. W is you know, it's what desirable success, right? B, it's undesirable, and N. Okay, N is the size of my sample. So this means desirable, undesirable, sample is N. Success, failure, sample size N. Calculate expected value. Else, how many successes do I have on given those parameters? And how is your Kafka reading going, guys? Kafka and the other thing? How are we progressing? Okay, Naomi, that's wonderful. All right, so what's going on, guys? Only one person, so let's do it. How many successes can we have? I mean, we can imagine sampling in order, first, second, third, fourth, right? Doesn't matter. You can imagine at the same time or in order, doesn't affect anything, yes? Same probabilities. So x1, x2, xn are, did I have success first sample? Did I have success second sample all the way to the nth sample? Now, the expected value of a sum is the sum of the expected values, even though the x's here are not independent. You agree? They are not independent. Because if I have a success on x1, I have a little bit less chance of success on x2. Yes? I remove a possibility of success. So then, but it doesn't matter. If I just focus on the second position or the first position, right? It's the ball that I will likely to pick is equally likely to be any one among available ones. So that means that the probability of success for x1 is w over w plus b. And therefore the expected value of x1 is 1 multiplied by probability of success plus 0 multiplied by probability of failure. And that means it's just the probability of success. Yes? And that will be, guys, do you see that there is nothing special about 1? If I focus on the kf sample, then it's equally likely to be any one of the available balls, right? If I do the experiment again and again and again, the kf one is equally likely to be any one of the available balls, the symmetry, right? So there are w plus b balls, any one of them is equally likely to be the kf. So it's the same for all of them. All of them have the same expected value, so I multiply it by n. The expected value of 1 I multiply by n, and as Naomi said correctly, it's n times the probability of success. It's the same as for the binomial. The expected values for hypergeometric and binomial are the same. Do you see that? Number of trials, probability of success. Probability of success is w over w plus b here. That's why it's written this way, but it's the same as for the binomial. How about the variance? Variance is do you want to calculate it, guys, or? is variance of the sum of the variances here?
Would it just be n times w over w plus b times b over w plus b?
Well, you have to be careful because, again, we cannot say that variance is the sum of the variances. Do you see that? Because they are not independent. We could say variance of the sum is sum of the variances only when they're independent. Expected value works all the time, but variance, we verified, does not. So what's the formula for variance? Here it is, guys, right? It's the summation of the variance plus all the covariances possible. You understand? So it's variances plus all covariances. So calculate it, and we'll see. It looks like some people escaped from me. All right, let's go ahead, do it together. All right, so we need to add up all the variances and we need to calculate all the covariances. How many covariances will we have? Think about it. How many covariances will we have? So it's 1, 2, 3 x's, right? Covariance is when I combine one x against another, not equal to it, right? And you have all combinations, right? From one from here, one from here. How many combinations will we have? One from here, one from here. Think about that are not matched, right? They cannot be x1 and x1, right? Must be x1, x2, or x1 and x3, right? How many combinations can I have? Well,
would it with x? It has to contain x1.
no, I mean no. I'm saying one from so covariance. It's like it's you have the red x's and you have the blue x's. That's how I imagine it, right? Covariance, it's like a little bit like a product, right? So how many covariances do you have? Well, very simply, just take, come on, can you do it? Come on, guys, do I need to put the words in your mouth? How many of them?
If we're choosing 2, then would it just be n choose 2?
Wonderful, n choose 2, but n choose 2 means smallest here, largest here. It could be the other way around, so it's multiplied by 2, right? N choose 2 multiplied by 2, do you see why? Because when you say n choose 2, you're saying smallest is here, and the larger one is here.
Oh, because covariance is equivalent for both x, y, and y.
Yes, it is equivalent for both, but also because we will have when I do the variance, it's very similar. It's what is a multilinear or bilinear function? It's really a generalization of product. Okay, so if you study linear algebra, covariance is a bilinear function, or I think that's what you call it, right? So so then what we have is, first let's calculate the expected value of x1 squared. Okay, what's the expected value of x1 squared? That's the same as the expected value of x1. It's w over w plus 1, right? And so what is variance? Variance is w over w plus b minus that number squared, and we have this situation, right? We have w over w plus b times b w plus b. It's the variance of one of them, yes? Now, what about the covariance of one of them? Without loss of generality, I can just pick 1 and 2. They're the same, right? I pick 1 and 2. So the expected value of x1 and x2, right? That means I have success on x1 and success on x2. There must be both successes, right? So that means w over b plus w plus b, w minus 1 over b plus b minus 1. You see? That is the expected value of their product. And so covariance is simply the expected value of the product minus the product of the expected values, which are the same. So it's minus this number squared. I simplify it and I have something. So then what I have is variance is, we have n variances, where I multiply it by n. And and then I add to it the covariances, which is n multiplied by n minus 1, because it's n choose 2 multiplied by 2. So it's n times n minus 1 times 1 calculation of covariance. And this is the formula I reduce it to. You understand the idea? All right. I suppose our time together has come to its finish, unless, of course, you want to stay longer with me. I was, my God, today from morning until now. First, I helped somebody with Russian, then with probability, and then again probability. So all day today since, I think, 12 that I'm on this platform. So, guys, read the novels that I suggested. It's very weird. Kafka's novel is very weird, right? All right. Take care, guys. If you're leaving, or if you have questions or want me to explain something, stay a bit longer. I'm stopping the recording.